Okay, so good day class. Today we are going to explore the analysis of doubly reinforced beam. So as it was emphasized on our previous topic, singly reinforced beam. So those concepts are only just for exploration and theoretical concepts that needs to be understood. But in the actual, there is no such thing as singly reinforced beam. So always we can see that in the plan, both tension and the compression zone are reinforced, mostly in reinforced concrete beam. So in here, we're going to integrate the compressive reinforcement because before we have explored the tensile reinforcement only. So doubly reinforced beams are beams that contain both tensile and compressive reinforcement. Compressive steel increases not only the resisting moments of the concrete sections, but also the amount of curvature that a member can take before flexural failure. So there will be an additional curvature resistance of the beam before the failure, aside from the additional moment that it would provide. Compressive steel is very effective in reducing long-term deflections due to shrinkage and plastic flow. So additionally, our compression reinforcement will benefit the beam in terms of the long-term deflection. Okay. So the analysis of singly reinforced beam will be directed to doubly reinforced beam. So we're going to analyze if the moment capacity of the beam of the full reinforcement at raw max is no longer sufficient to resist the required load. So hence, we can reinforce or consider compression reinforcement. So here we can see in the figure that the first diagram here is actually the singly reinforced beam only referring to AS. AS refers to the tensile reinforcement as we have emphasized previously. Now, if we have another reinforcement, compressive reinforcement is normally expressed in terms of AS prime. So, on this first diagram, we can see that the compression block is being paired to AS1 and AS prime is being paired to AS2. We note here that AS is broken into AS1 and AS2 to facilitate the analysis, because on this stress diagram we can pair only the compression block to the tensile block to emphasize that this is the moment caused due to tensile reinforcement. And if this will be at full reinforcement, hence your loading is still greater than the moment capacity, thereby AS prime will be needed. Okay. As a matter of detailed analysis, let us refer to this beam. Let's say this beam is reinforced under tension, denoted by AS. And of course, that AS will be the effective depth measured from the top fiber up to the reinforcement. And as usual, we have this B, or the effective width of the beam. And because of this tensile reinforcement, it shall cause a tensile force, where that force will be resisted by a compression block, which results to a compressive force C. While this block would be extended vertically at the depth of compression block denoted by A. Now, this block draws only 85% of the strength of concrete. Now, this distance is D minus A over 2, while those forces will cause mu on this diagram. Now, let us consider a compressive reinforcement here, denoted by AS prime. And of course, that reinforcement shall also produce another compressive force. Let us denote now these two by C sub 1 and C sub 2. Likewise, this moment here will become mu1. Now, granting that we have C2 here, there must be an equivalent tensile force to counter this C2. Therefore, this will be denoted as T1. Likewise, this C2 and T2 will produce a couple moment, say mu2. Now, these are the premises of the doubly reinforced beam. We'll just take note of the forces like C1, which is equal to 0.85 FC prime AB. AB here is the area of the concrete block, while T1 here is ASFY. So let us take note that this diagram is assumed to have a full reinforcement, meaning it has reached the raw maximum. That is why we do not need to assume that Fy could yield or not. So in doubly reinforced beam, it is always assumed that Fy is the tensile strength of T1, it's no longer assumed to be Fs, because it is always yielding. It is because that at this condition, our rho is greater than rho maximum. So we emphasize here that at this diagram, we always have Fy. So proceeding now to the next stress diagram, C2 here will be equal to AS prime, whether Fy or AS prime times Fs prime. So it simply means that the compressive reinforcement could yield or not. Now, the counter force for C2 is tensile 2, which is equal to AS2 times Fy. So, this should be denoted by AS1. So, likewise, the same as T1, T2 always yields. So, as you can see, T1 and T2 here are tensile reinforcement that is always yielding. Now, we need to check Fs prime every now and then in the design or investigation, particularly in investigation. So we need to understand what will be the formula to be used in order to come up with Fs prime. In that case, class, we just need to recall our strain diagram, which will now be involving AS prime, or the compressive reinforcement. So in the diagram, we need the neutral axis, and then we draw a straight line here. We need to put here the strain for concrete, which is 0.003, while here the steel strain, which is Fy all over 200,000. Now this line is the corresponding strain for the steel compression. Let's say that is strain prime, which should be equal to Fs prime all over 200,000. Now we utilize this triangle for ratio and proportion to involve these terms. So we'll be needing here distances. And we know that the distance of the neutral axis up to from the topmost fiber, this is C, alright? And then normally this is D prime. So the clear cover of this reinforcement, and then therefore this distance here must be C minus D prime. Therefore we are now ready to apply ratio proportion. We can say that C is to 0.003 is equal to C minus D prime as to the strain of the compressive reinforcement. So further, we're going to cross multiply. So C minus D prime times 0.003. And then the strain of the compressive reinforcement times C. So further, this 200,000 will be cross multiplied to 0.003 and becomes 600. We're going to pair that to C minus D prime. And what is left on the other side is Fs prime times C. Now we divide both sides by C. Hence Fs prime will now be isolated with this formula 600 C minus D prime all over C. Now these are the concepts that we need to apply in design and investigation of the beams involving doubly reinforced. Now let us proceed to the details. Let's say we have the design of doubly reinforced concrete beam. We expect the following given. Of course, the parameters, string parameters, the required moment, or if not, the loading. So if the loading would be given, we translate it into the moment required of the beam. We normally also have the beam cross section in terms of B and D dimensions. And of course, the clear covering of the concrete will be in terms of D prime. So in this case, we need to acquire the required tensile reinforcement as well as the compressive reinforcement. As we emphasized a while ago, this MU1 here is computed to a configuration wherein T1 will be yielding. Therefore, T1 here is equal to AS1 Fy, wherein AS1 will be calculated from this expression rho max BD. Then out of that, we perform C1 is equal to T1. We substitute C1 0.85 as C prime AB, while this is set to be AS1 times Fy. So it is always expressed as Fy. So there is no assumption in here. So we observe that A will be computed here, and if A will be known, C will be also determined by this formula. Okay, so now that we have known A here, we can now compute for MU1, which can be computed by the tensile force or the compressive force. Anyway, all of the needed parameters are already available. So notice that the first unknown were already determined, or the partial solution for AS is already determined by this AS1. So of course, if MU1 will be known by the premise of MU as the sum of MU1 and MU2, MU2 can be derived right away by getting the difference of MU2 dot MU1. So MU2 shall be determined, and we can relate MU2 to that of the T2 by this expression. This is equal to phi T2 times D minus D prime. I'm actually referring to this distance, D minus D prime. So we take moments at C2, and then we have T2 times D minus D prime. Now we expand T2 in terms of AS2. Of course, knowing MU2 in here, we can now compute for AS2. So observe in here that we always use Fy to pair AS2 to that Mu2 because T2 is a part of the tensile reinforcement which is always yielding in the case of compressive reinforcement or doubly reinforced concrete beam. And at this point, we have already completed the tension reinforcement by simply adding AS1 and AS2. Moving on to the compressive reinforcement AS prime, and granting that we have C here available, therefore Fs prime can be predetermined already by this expression. And of course, Fs prime will be readily available. So all we have to do is to compare it with Fy. Now, if Fs prime is less than Fy, therefore, the compression reinforcement does not yield. Hence, in this case, we use Fs prime in this expression to come up with As prime. And of course, we need the value of C2 here by simply equating C2 is equal to T2. So we note that As prime can be paired by either Fs prime or Fy depending on the result of Fs prime. And we have no problem to the right-hand equation because As2 is already determined. And we can get the value of As prime right away in here. Now, in contrary, if Fs prime would be greater than Fy, therefore compression reinforcement yields. Hence, we use Fy in this equation. So at this point, we have actually obtained what we need, which is As prime. So this is the concept of the design of doubly reinforced beam. Now for investigation, it is expected that once again, parameters are given here. And normally, dimensions are given in terms of B and D, as well as the concrete cover D prime on top of the reinforcement. And in here, both reinforcements are given, As prime and As, and we are required to determine the moment capacity of the beam. So normally in problems, this moment capacity requirement would also be extended to the load capacity of the beam. At any rate, the moment capacity would be enough reference or basis for the loading. So in here, since As prime and As are given, therefore our focus will be on this steel reinforcement. Hence, we should be aware of those connections between As prime and As. So the first connection of this As prime to As will be in this diagram, where C2 is equal to T2, or the compressive force caused by the reinforcement will be equal to T2. So we write C2. C2 here is As prime, Fy, or Fs prime, while T2 is As2, always that this is Fy. Now, if compression steel would yield, in this case, your formula will become As prime Fy is equal to As2 Fy. Therefore, it would follow that As prime is equal to As2. Of course, starting from this procedure, we have to make this as an assumption and then check it later. Now, since we have known As prime, that will be equal to As2, therefore, we can now work with this As is equal to As1 plus As2. So we have known this and this one. Therefore, we came up with this value As 1, which is actually needed in this equation. We expand both of the left and right side of the equation and solve for A. And from here, we will be having a value for C and a value for Fs prime, that is 600 C minus D prime all over C. Now, if Fs prime is greater than Fy, we have a correct assumption. So therefore, all of these values here are valid values. Hence, the moment capacity can be computed right away by taking moments at t. We have first this one, C1 times D minus A over 2 plus phi C2 D minus D prime. Now, if Fs prime is less than Fy, we had a wrong assumption. So in this case, we'll go back to the first step, that C2 is equal to T2. And by the way, by this assumption, we note that AS2 is not equal to AS prime, just as this case. Now we expand both of the terms, and of course Fs prime will be expanded by its formula in terms of C. We retain the right hand side of the equation, AS2 Fy. And at this point, notice that we have a lot of unknowns, AS, C, and C. So AS prime is actually given here, and AS2 and C will not be available. So we have no way to continue with this one. Kasi AS2 and C are not available. So therefore, we're going to explore on this diagram here. Hence, we should always remember that if your assumption is wrong, we use this equation that T is equal to C1 plus C2. So in this case, there is no more breaking down of T1 to T2. So T is already in terms of AS, not AS1 and AS2. So we have this first term, and then we have the second term. So if you notice, this is in terms of C. I have just replaced A with beta 1C. And we have here the second term on the right hand side of the equation. This is in terms of C also, whereas I have just replaced Fs prime in terms of C. So notice that in this expression, AS is known, Fy. So the strength parameters are known, C is unknown here, B is known, AS prime is known, D prime is known. So therefore, we have a single unknown which can be calculated in this equation, which is C. Then out of that, we will be having the value of A. So, of course, C and A will be resulting to Fs prime, because Fs prime is just equal to your in terms of C. So of course, knowing all of this, we can already utilize or go back to this equation to solve for the moment capacity. But take note that C2 here will be in terms of AS prime, Fs prime. So for the case that Fs prime is less than Fy. Okay, so those are the needed concepts in design and investigation of doubly reinforced beam. It is just a matter of a procedural analysis. Thank you, and I hope you will apply this in the problems that will be given to you today.